Hi everyone. So yeah, I'm Steven Tuzar. I'll be chairing this morning session, morning for Singapore at least. So today we have as a first speaker we have Liang Jiang from University of Chicago, then Rafael Alexander from RMIT and Kyungju No from AWS, and Dmitry Matrukevich from NUS. So every talk will have a duration of either 40 or 25 minutes, plus 5 minutes of questions that will be selected from the chat. If your question is not selected and that we are running over time, you can ask them on the Slack for the BBQ conference. And other than that, we'll have a break, a 15-minute break at the end of the first two talks. And so for now, we will start with Liang Jiang from University of Chicago, speaking of an overview of Bosonic quantum error correction and various applications. The floor is yours, Liang.
Okay. Hi, Steven. Thanks for the introduction. And well, maybe good morning, good afternoon, and good evening, everyone. It's because people are in different time zones. And so, well, I guess that maybe first I would like to thank the organizers for organizing this workshop at a difficult time. On the other hand, I think it probably having it virtual maybe allow more people to actually attend the discussion. So today I'll maybe as the first talk, maybe I'll give an overview about bosonic quantum error correction and discuss about the various applications. So maybe just at a broader scale, like we're talking about quantum information processing, and the bosonic modes actually play a very important role. It can be used for computation, communication, metrology, and quantum simulations. And one of the major challenges to use bosonic system to process information is excitation loss, because it doesn't matter whether you store it in photons, phonons, or different or atomic ensembles, these excitations or the atoms, they may lost from the ensemble. So therefore, that's one major challenge is that we want to store information actually hopefully be longer than the typical coherence time of the modes. So in order to do it, we actually try to see if there are good ways to use error correction to do it. And one key idea of the error correction is actually to introduce redundancy so that we will be able to differentiate whether an error or it's a logical operation. And for qubits, we only have 2 levels. So a way to introduce redundancy is to have multiple copies of qubits. And that allows us to check whether or not a qubit being flipped or have a dephasing error. And for bosonic case, like for example, harmonic oscillators, we actually can have redundancy even with a single bosonic mode. For example, if you think a single harmonic oscillator, which can be decomposed in written in different orthogonal Fock states basis, then there's actually an infinite dimension, which by itself does have a redundancy, which might be useful for error correction. And moreover, for bosonic systems, there is actually the error pattern is actually more restricted because typically practical relevant errors, including loss and dephasing error. So if you have excitation loss, every time the excitation is leaked out one by one. So there is some structure in the error which we might be able to take advantage when we design error correcting codes or detecting a photon loss errors. And the dephasing error, there's also a similar pattern, which at least the photon number do not change drastically. Or in the phase space, actually the error would not immediately move from one coherent state, say alpha, to the other coherent state, negative alpha. And this actually allows us to design a good error correcting codes, which are hardware efficient and can correct dominant errors, which are practically relevant. And it has been a long history, maybe for more than 2 decades, studying bosonic codes, including using Fock bases or higher order Fock states. Or you can think as a superposition of coherent states, or use a position momentum eigenstates, or hybrid between bosonic qubits and bosonic modes and the qubit systems. And if you look at the history, basically there is around the early 2000s, there are lots of developments in the Bosonic codes, and more recently with the emergent exciting development on superconducting systems, we can actually perform deterministic non-Gaussian operations with help from the Josephson effects. So that also excites lots of new design of Bosonic codes. And in addition, trapped ions also have these controls. So you probably will hear more talks on using superconducting circuits or trapped ions, or even optical systems that can potentially allow us to prepare Bosonic codes and also use it for error correction. And so probably maybe let me just focusing on 3 aspects on this. The first is that how do we design a Bosonic code using single Bosonic mode to correct loss errors? Then I'll talk about using Bosonic codes for different applications. And at the end, if there's still some time, I'll talk about how to achieve a robust control over Bosonic modes, not limited by the additional ancilla. So maybe let's start with just a single Bosonic modes, how we use Bosonic modes to correct errors. So one way to think of it is that maybe we can borrow something from classical error correcting codes. And one well-known classical error correcting code is the phase shifted keying. So we know that a coherent state, which you can use 2 real numbers to describe a coherent state. A coherent state alpha has amplitude, which is the magnitude of alpha, and has a phase, which is this complex angle associated with the coherent state. So in the presence of photon loss or attenuation, typically the coherent state's amplitude may decrease, but the phase of the coherent state is preserved. So classically, we can store information in the phase of a coherent state, and that leads to the phase shifted keying. So for example, here on the left, you have this phase quadrature, phase diagram. You have 4 different coherent states with the same amplitude, but the phase difference between different neighboring coherent states is different by 90 degrees. And because there are 4 coherent states, you can encode 2 classical bits of information. And we can extend this to a quantum encoding, which is introduce redundancy by encoding, instead of 2 quantum bits, you encode just 1 quantum bit in the even photon subspace. So you can design the logical 0 state to be symmetric combination of alpha and minus alpha, or the logical 1 state to be the symmetric combination of I alpha and the minus I alpha of coherent states. So these states, definitely they are not Gaussian states, because you see actually they are negative fringes in the Wigner function, but they're actually useful because you can use parity to track whether or not there's a photon loss. And you can even restore the original information after detecting photon loss. So there will actually be more talks by multiple people, from multiple speakers from both theoretical and experimental perspectives on the CAT code. So I want to point out that the CAT code has a unique property, is that because the coherent states alpha and minus alpha are well separated in phase space, while the typical errors only kind of have some preserve the locality of the phase space. So therefore, actually the CAT code does have a biased error. So it's unlikely to go from a one CAT code to go to the other CAT code. So therefore, this biasedness of the error actually could be advantageous for us to design hardware efficient fault-tolerant quantum computing. So this is one code which it seems has a connection with the classical phase shifted keying. And in the classical world, we have another code which is called the quadrature amplitude modulation, which not only encodes information in the phase as we had in the previous slide, you can also encode information in the amplitude, assuming you know how much loss is the error channel. So in this case, you can actually put in an array of coherent states in your phase space and encode the information using these array of coherent states. And the extension to the quantum case is actually you could design a 2-dimensional subspace, which is spanned by from this array of coherent states. And that actually leads to the Gottesman-Kitaev-Preskill state, the GKP state. The GKP state was designed about 20 years ago, and at that time was original goal is actually to correct the thermal noise, but it turns out the GKP state is also a really excellent code that can correct the photon loss errors as well. The reason is actually quite simple, is that if you have photon loss, you can introduce additional phasing sensitive amplification so that the loss error can become thermal noise where the GKP code can correct. So there will actually be a lot more discussions in this conference, with talks from both theory and experiments, and with experimental demonstrations in both superconducting circuits as well as trapped ions. So there will be actually lots of exciting developments that you will hear from the later of this conference. So another code, which actually I don't think they have a classical correspondence, is this kitten or binomial code, which was invented by Steve Gervin and the collaborators. And you see that different from the GKP or CAT code, this code is actually written expressed in the photon number basis, Fock basis. So we know Fock states is non-classical. So here actually we have Fock states with some reasonable choice coefficient for combinations. So for this kitten or binomial code, it actually can also be used to correct photon loss errors. So there will also be some talks about how to use kitten or binomial codes to correct photon loss and also achieve a robust control. So just as like a quick summary about different choice of bosonic codes, we have CAT codes, GKP code, and binomial code. And one way to represent these codes is actually to introduce some like a code fingerprint, which is actually fully characterized by the Wigner function of the code space projection. So basically you can define the projection operator to the code space and plot the Wigner function. And there is a 1-to-1 correspondence for different codes and different Wigner functions of the projections. So here you see the CAT code, and that actually has recently been demonstrated using, well, not exactly this 4-leg CAT. There are like a recent demonstration using 2-leg CAT using superconducting circuits. And there are like biasness in the errors which have been observed experimentally. And the protection of the CAT code can be achieved either using autonomous error correction or using measurement and feedback controls. So I think that one of the few highlights for the CAT code is the biasness of the error. And also you can design a full set of universal gate set that preserves the bias of the error, which can lead us to design hardware efficient fault-tolerant quantum computing. And also, there are some ideas which we think it's possible to design robust control of the CAT codes with Ancilla, which could be noisy, but the control does not suffer from the noisy Ancilla. So in the middle, we plot this GKP code. I showed two kind of like projections of GKP. One is for the square lattice, the other is for the hexagonal lattice. And we think that the hexagonal lattice probably could achieve like a slightly better performance because it's a more compact packing in the phase space. And also there are recent experiments in both superconducting circuits and trapped ions, which show that the GKP code can be demonstrated experimentally. And the performance for the GKP code is actually, it's almost approaching the break even. Basically, it's almost as good as the best code that you can have without error correction. And also the GKP code is really like excellent in correcting like loss errors. One example is even with 10% loss, in principle, GKP code can restore the fidelity to 99.99% fidelity. And in addition to like for quantum information processing, GKP code can also be a really good displacement sensor. Because of the nature of this periodic structure, and you can design the GKP code as a stabilizers of two commuting operators, you can sort of simultaneously measure position momentum modulo square root of some constant, which could be useful for sensor. And as the extension, you can use that sensor to design new bosonic codes so you can encode oscillator into multiple oscillators, which would be useful potentially for quantum simulation in the long run. And the last one here I'm listing is a binomial code, which has been experimentally demonstrated using superconducting circuits, and also with a performance which almost approaching the break even. And there are also discussions of seeking the possibility of doing autonomous error correction, which I think, sorry for mistake. Here, the autonomous error correction is actually should be in the GKP code column, which people are designing reservoir engineering to stabilize GKP code. But for the binomial code has also unique features. For example, it can be a really good sensor to sense the Kerr effect in the presence of photon loss. And also there are possibilities of performing robust controls using noisy ancillars. So you'll hear a lot more in the later part of this conference about the different properties and different like advances on these different codes. So maybe let me now switch to kind of like the question about the applications of these Bosonic codes. So first, I will have a brief overview about the quantum computing aspects of Bosonic codes. So here I'm just showing kind of like the complexity of how we actually approach like a fault tolerant quantum, go towards fault tolerant quantum computing. So we may want to start with some like a quantum non-demolition measurement. Then we'll do the error correction and hopefully demonstrating like a break even and do logical operations. And in the longer run, we want to do fault tolerant quantum computing. And there are some key challenges, which including how we suppress the system noise and extract the entropy from the system, and how does the error behave at the logical level, and how to achieve robust control with noisy ancillars. And on the right-hand side, here you see actually like just a summary of incomplete list of publications, which related to some of the key advances of how to achieve like a parity measurement, all the way up to how to achieve like some fault tolerant like quantum gates. So some of the references which I highlighted in bold font I think there will be a talk like to detail these advances. But I guess related to some of the questions, like how to extract the entropy and perform error correction. I think generally there were two types of schemes. One is the measurement and the feedback approach. So basically you perform a measurement and use your classical computer, or could be FPGAs, to do a real-time feedback to decide how to suppress or undo the error. And the other approach is the engineer dissipation, which might have an advantage that you can save the delay due to these classical operations and really design the system so that the reservoir of the system will automatically cool the system to the logical states and suppress errors. And also about the second question about the behavior of the error at the logical level. This is, I think, it's getting more and more, it's getting more attention because, for example, the CAT code, there is actually a biasness in the error. And this is actually very important because if we could have a highly biased error, for example, suppose we only have dephasing error, no bit flip error, then we can just use the simple repetition code at the next logical level, then we can achieve fault tolerant quantum computing. So this might point another shortcut, which might enable us to achieve hardware efficient fault tolerant quantum computing. And I think that probably there will be more like theory talks along these directions. And I guess probably Earl Campbell might talk about this direction as well. And the last part is that usually to achieve a control bosonic system, we need some additional non-aharmonic systems such as transmon or some of the ion degrees of freedom. And for example, the transmon might be quite noisy compared to the cavity. So there is a question about, okay, how we actually improve the performance, how to use a transmon for nonlinearity, but not suffer from its decoherence. So it seems that there are design principles combining quantum error correction and quantum control. For example, we can design some like error transparent or more generally path independent gates to achieve a robust control, not suffer from the noise of the ancilla, which if I had time, I'll maybe talk briefly about this at the end. So I think you will hear a lot more about the quantum computing in the conference. So, but let me also point out there are more applications. So for example, we can also use Bosonic codes for quantum communication, because just think like every WIP package we send over the fiber channel is actually a Bosonic mode. So it's natural to think, can we design more efficient Bosonic codes for quantum computing? And I think one interesting direction would be, okay, maybe we can design good Bosonic codes, and then maybe we can do frequency conversion between optical and microwave and use our capability to process these or create or process non-trivial Bosonic mode in the Bankrif mode, and then convert back to the optical so it can send over long distances to the next repeater station to achieve like a one-way long distance quantum communication. And there have been some like more recent developments, both from my group and also from others like Alexander, like Fukui and Peter Van Lok. We're thinking about, can we use the GKP code or maybe concatenate with other qubit codes so that we could have this concatenated continuous variable Bosonic codes and the discrete variable qubit code. And the feature for this is that this concatenation might be quite beneficial. For example, the lower level of bosonic codes can actually, the syndrome measurement can give us analog information, which can inform us how to boost the performance of a second level, the discrete variable code. And one feature we see is that even if the second level code is only detecting errors, but assisted by this analog information, this error detecting code might behave as good as error correcting code, which is actually like can significantly boost the performance and reduce the resource overhead. And another question is more fundamental, is that for the bosonic codes, since the fiber communication channel is the bosonic modes, can we design efficient bosonic codes to achieve the channel capacity? Because this is kind of in the classical world, it took like people like almost half a century to design like a good classical error correcting codes, now like LDPC code or polar code, to approach the Shannon channel capacity. And for the quantum case, this might become a relevant question down the road. So we might want to explore if there are good bosonic codes, which maybe in the long term that we can demonstrate to approach or get the maximum use of the quantum communication channel. So the third application is related to quantum metrology. And as earlier I mentioned, maybe binomial code could be used for sensing Kerr effect in the presence of photon loss. And here I can mention another example, which is actually the GKP code. So GKP code, and here let me give it a bit more quantitative definition. And here I'm just to consider a GKP state, which is a state stabilized by two operators. So we all know from quantum mechanics that we cannot simultaneously measure position and momentum because these two quantities, they do not commute with each other. However, the commutator is a constant, which means that if we make a closed loop in the phase space by displace along position or along momentum directions and displace it back, we can enclose an area. If the area is integer multiple of 2 pi, then actually these displacement operations, they commute with each other. Okay, because the area corresponds to there is actually a geometric phase, and that geometric phase is actually once it's equal to 1, then basically it doesn't matter whether you displace left first or you displace upward first, those displacements commute with each other. So for example, here you can define the SZ and SX corresponds to displacement along the position or along the momentum quadrature. And by choosing the coefficient carefully, the enclosed area will be integer multiple of 2 pi. And here we just choose it to be 2 pi. So they commute with each other. So if you have two commuting operators, you can define co-eigenstates of these commuting operators. And turns out that for this definition of operators, there's only a single eigenstate which has eigenvalue +1 for both of these operators, which is called the GKP state. And if you think physically, what are these operators, SX and SZ? It corresponds to make a discrete displacement along position and momentum quadrature. And if it's a state, which is the eigenstate of the displacement, which means it must have a periodic structure in the phase space. So the GKP state turns out to be like a periodic in both position and momentum with a period of √2 pi for this definition. And moreover, because position and momentum, when you exponentiate, you get these operators, they commute with each other. It means we can simultaneously measure these two operators. And the measurement from these two operators, it actually corresponds to the position and the momentum modulo √2 pi. So if the position momentum you want to measure is actually have some small displacement, which is much less than √2 pi, then basically you can measure those small displacements up to modulo √2 pi. And this is actually could be useful for sensing applications. So here I'm considering just a one-dimensional GKP state, which do not encode information. But later in the talk, you'll hear like people talk about the GKP state, maybe the area enclosed is an integer multiple of 2 pi, then they can encode a qubit or qubit using GKP state. But just giving some intuition how the GKP state look like, on the left is just a color plot of the GKP state in the phase space with which has combinations of positive and negative parts of the Wigner functions. And on the right side, this is the GKP state which has a finite energy, which have some Gaussian envelope And that tells, but you can see there are still like these spikes, which kind of might remind you there's a periodic structure in the phase space that can be used for sensing. And just what we will need later on is actually GKP state allows you to simultaneously measure position momentum modulo 2 pi. So that actually leads to the question about the quantum simulation and sampling. So here I'm showing the figure, which is about the boson sampling, which was proposed by Scott Aronson and collaborators, which pointed out that even with just beam splitter and phase shifters, if you have Fock states coming in and you have photon number measurements, that measurement outcome, the probability distribution might be very difficult to obtain classically. And moreover, I think we can use that similar idea extended to simulating vibrational structures from Kondo factors of molecules. And I think Steve Gervin will talk about how to use superconducting circuits to simulate the molecule vibration and get the Frank Kondo factors from the simulator based on superconducting systems tomorrow. So I will not get to that detail on that. But I want to point out that one of the challenges for boson sampling is actually when you have excitation loss, then it's actually an open question at how much loss you can tolerate for boson sampling to maintain the quantum supremacy. And there are like lower bounds, like to say like, okay, below certain value, then you will not be able to achieve supremacy, but it's actually still an open question, which is also a practical challenge. So this motivates us to think, oh, can we use bosonic codes to actually help or boost the performance of boson sampling? And so when the goal is actually, we want to perform error correction against excitation loss errors in bosonic system. But at the same time, we want to preserve the boson statistics at the logical level. Okay, so the challenge is actually that people already proved no-go theorems, maybe more than like almost 20 years ago. So basically, the Gaussian encoding cannot correct loss errors. So here, Gaussian encoding means that if you just use coherent states and beam splitters, two-mode squeezers, you will not be able to achieve a code which can simultaneously correct loss errors or preserve the bosonic statistics at the logical level. So in order to go around this no-go theorem, the trick is basically change the conditions in the statement of the theorem. So here it says Gaussian encoding cannot. So what if we have non-Gaussian encoding? So we need some ingredient which is non-Gaussian. And it turns out that actually like actually this idea will come up from by Ken Zhu. He actually say, well, what if we use GKP state as a non-Gaussian ingredient? Then he actually found a scheme which can correct loss errors and at the same time preserve the bosonic nature at the logical level. So the idea consists of two parts. The first part is that first we need to convert the loss errors to the added thermal noise error. And the second part is that how we actually use non-Gaussian GKP states to correct the thermal noise. If both are possible, then we can use non-Gaussian GKP states or some extensions of that to achieve correcting loss errors while preserving the bosonic nature. So first, let's just show like how we can convert loss errors to added thermal noise. So here is a simple schematic. Suppose you have a coherent state. In the presence of a loss, the amplitude of coherent states will be attenuated. But the uncertainty is still like 1 unit of uncertainty associated with the quantum fluctuations. So now the second step is you perform a phase-insensitive amplification, which will increase the amplitude, but at the same time, the noise also gets amplified. So therefore, you see the uncertainty blob gets increased as well. So the final state is no longer a pure coherent state, it's a mixed displaced thermal state. So therefore, we say that actually the state we get will have added thermal noise. Even though we start with, actually the channel initially have loss, but with amplification, it becomes thermal noise. So basically, we can convert pure loss error into thermal noise. So the next step is, can we actually correct the thermal noise while preserve the bosonic nature? So in order to correct thermal noise, we basically need to measure what is the added thermal noise to the position quadrature and what's added thermal noise to the momentum quadrature. And then one way to do it is actually if we know the added noise is much less than square root of 2 pi, we just want to get that information in terms of modulo root 2 pi. And this time GKP states come into play. Because, for example, I have incoming states. I can use a GKP state that as ancilla and perform a control sum operation, which you can think it as a unitary evolution with a Hamiltonian as Q1 times P2. And with that evolution, you can measure the GKP states in the Q quadrature. And that will tell you the initial momentum, initial quadrature, Q quadrature of the initial input states modulo root 2 pi. So that allows you to measure the position modulo root 2 pi. Similarly, you can also have a GKP state that it evolve coupled to a system with a different Hamiltonian, and you measure the momentum, you can measure momentum modulo root 2 pi. Okay, so combined with these two, then you can actually, and we'll use this as a later to extract the noise. So here is actually the encoding, which introduces some non-Gaussian ingredients with the GKP states, and the psi is an arbitrary bosonic state. And what the encoding does is it perform a control sum operation between the unknown states and the GKP ancilla state, and then perform some squeezing or anti-squeezing for the two modes. And this is the encoding. As you see, apart from the GKP ancilla being non-Gaussian, the rest of the operations can be implemented using bilinear Hamiltonian. So this gives us a GKP repetition code. So here is just to illustrate how GKP repetition code works. So you let the GKP repetition code go through a channel which may have added thermal noise. Then the decoding is essentially the inverse of the encoding. If there's no noise added, you get a perfect decoding, because as the inverse of the encoding, you will get a tensor product of the unknown states with this GKP ancilla. So if there's no noise, you get identity operation. So if there's noise added in the first channel, then what happened is the noise will propagate and be modified with the squeezing operation and then propagate to both channels. But because this control difference operation only propagates noise of this P quadrature to the second channel, then you can perform a position, a momentum measurement modulo 2 pi to suppress the P quadrature noise so that only the Q quadrature noise left behind. But because of this squeezing operation, the Q quadrature noise gets squeezed by a factor of lambda. So it can suppressed to a small number, sigma squared. So sigma is the magnitude of noise, which is much less than 1. So therefore, sigma squared can be even smaller. Now suppose actually the second channel also have noise, but it's independent from the first one. Then this time the noise will also propagate, and we actually perform a Q quadrature measurement on the second channel to extract that noise. And because of this control sum, a control difference operation, only the noise of the Q quadrature from second channel propagate to first channel, we can actually compensate most of that noise so that only the noise get to the first channel is only suppressed, and the P quadrature noise only suppressed to the sigma square. So therefore, we can show that both P and the Q quadrature noise get suppressed to the second order. And then Kenju did this numerical simulation to verify that indeed, after this recovery, the both position momentum quadrature noise gets suppressed quadratically. So here is a log-log plot. You can see the slope equal to 2 indicates the errors being suppressed to the second order. And you can extend the design to more on this repetition code. And the more repetitions you have, the higher the order the noise you can suppress. And if you go to nth order, you can suppress it even more. Okay, and generally, you can replace this control sum with some Gaussian operations, bilinear couplings, like a two-mode squeezing or beam splitters as well. Then you will get actually generally called the GKP stabilizer code, because you can write down similar like stabilizer formalism for the code as what we did with the qubit case. And this will allow you to correct both noise in position momentum quadrature while preserving the bosonic nature at the logical level. So moreover, we could also extend the GKP stabilizer code to quantum metrology. For example, you can do distributed sensing while preserving the bosonic nature that might be entangled with some remote parts. and using GKP stabilizer code to correct local added noise. So maybe just as like an overview about the applications, we could use this Bosonic codes for computing, communication, metrology, and the simulation. So I think I probably have 5 more minutes. So probably I would just address the third question, which I think is practically highly relevant about the Bosonic system. Because one of the challenges in this Bosonic quantum information processing is actually typically we need Ancilla or the nonlinearity from the Ancilla to achieve a universal control. Because if we don't have Ancilla, typically what we have are beam splitters and squeezers and the displacement. That's not universal. So we need some like nonlinearity from the Ancilla, and usually the Ancillas sometimes can be quite noisy. For example, the transmon could be more noisier than the central system, which is just a 3D superconducting cavity, which is less noisy. So there's a trade-off. We have a central system which has excellent coherence, but limited control. On the other hand, we have Ancilla, which is noisy, but it actually allows us to achieve universal control. So the question is, is it possible to combine the two to achieve Ancilla-assisted quantum control, but not limited by Ancilla decoherence? Or another way to say it is that typically you can think of it as a hybrid quantum system, but we want to hybrid in a good way, that we borrow from the universal control from the Ancilla, but we don't suffer from the decoherence from the Ancilla, which is actually usually it's quite challenging. And most of the hybrid systems, people find that you always suffer, your coherence is limited by the worst part. But here we want to kind of overcome that challenge. So just the 2 remarks. One is that the conventional quantum control techniques like a spin echo actually failed in this case, because typically the Ancilla noise from the transmon, it's kind of white noise, and it increases the entropy. There is no way to echo it out. And the second is that the gate-based error correction actually does not immediately apply for such a Hamiltonian evolution system. Because usually when you do quantum gates, if you look at Niels and Chuang, they always assume you have a unitary, and after which you perform, there will be error. But here it's actually during the unitary evolution induced by Hamiltonian, errors are happening at the same time. And moreover, our information is encoded in the central system, so some error from the Ancilla could completely erase the information encoded in the central system. So therefore, we need to develop like new formalisms to combine quantum error correction and quantum control to achieve like a robustness against Ancilla errors while using the nonlinearity from the Ancilla. So, so you can, if you're from the experimental side, you probably can think that our central system could be a really high quality superconducting cavity, and the Ancilla is actually this transmon, which could be more noisier. Okay, and so it probably like might hurt some of these results in terms of error correction that achieved. This is the figure from the break-even error correction paper that using a transmon qubit to extract parity information, and they do the CAD code and they perform that. Indeed, you can get to like a break-even. But if you look at the break-even point, it's kind of like just a touch. And the natural question is, can we do better? But at that experiment, the limitation is actually when you try to measure parity, it introduces error to the system. That error is about the percentage level. It's because the gates for the parity measurement took about 1 microsecond, and the transmon coherence is about 100 microseconds. So therefore, there will always be 1% error. And similar, if you want to do universal control with the cavity system, you also suffer from this error because the gate took about a microsecond, and the transmon has a 100 microsecond decoherence, right? So therefore, it's kind of, there's a curse of this like a % error for most of the Bosonic quantum information processing experimental papers. And I think there's a way to get around it, which first has been demonstrated using this fault tolerant like parity tracking. The key idea is that when we try to measure the parity, the Ancilla may decay. But what actually Serge and others in Rob Shirkoff's group demonstrated is that we could design the Hamiltonian evolution so the Hamiltonian sort of commute with the jump error so that it become error transparent. So if a jump error happen in the middle, it's effectively as if the jump error happened at the end. So the ignorance of when the jump error happened does not play a role. So therefore, we can just need to detect and correct the jump error at the end, therefore to restore the information. And the natural question is, can we actually extend it from parity checking to universal quantum control of the bosonic system? And here, I think that probably I don't think I'll have time to get to all the details, but the key idea is something which we're all familiar in our classical mechanics, which is something called path independence, or in classical mechanics, it's kind of corresponds to a curl-free vector potential. So if you have a vector potential, you know that doesn't matter which path you go, the work that you do only depending on the initial and the final point. And here, it's the analogy is that sort of doesn't matter which path you go from this quantum trajectory evolution. What happened with the system is only depending on what the initial and final state of your ancilla system. So that actually leads us to this path-independent formalism, which was inspired by the earlier work by Eloy Capet on this error-transparent quantum gates. And I think that's probably like Liang and Serge will talk more on these topics in the experimental side. But I guess that I think I already used up my time. And finally, I would like to thank all the people that both experimentalists and theorists I collaborated with, and also the funding agencies that support this research. Thank you very much.
Thank you.
Right, thank you, Liang, for this talk. It was great. So I have a couple questions from the chat. So yeah, we have 5 minutes for questions because you're right on time. The first one is from Byron Bay Quantum, which I guess is one of the organizers. So probably Arnie, I guess. Since amplification turned loss into thermal noise, does that mean that, and it adds more noise, is it obvious that it makes it better and thus easier for the GKP code to correct? And so I would like to add something to that because I had a similar question. This amplification, phase-preserving amplification process can be thought as a unitary that entangles to another mode that you just choose to ignore, right? You trace over it. So it sounds like, is it an artifact of for calculation, or is it really something that helps to add this noise?
Yes, to that question, the answer is I think it's more like a conceptual thing that we introduced to help us to see the connection that the GKP code can correct loss error. But on the other hand, it's actually may not be required to do quantum error correction. Because there are like procedures which probably you might heard from Baptist, this like you can design engineer dissipation to correct the GKP code, and that procedure does not require amplification. And it's actually, I think that amplification actually limits our performance. And this is an open question, which we've been thinking for several years, but I think definitely there are better error correction procedures for GKP. Which so far it'll stay as a big matrix as a CPTP map from numerics. It would be nice if
sensing, for example, GKP to displacement. Is there a constructive way to go from a certain Hamiltonian that we know that we want to send something that couples to a certain operator, and then we add an error channel, and we can constructively design a code that will sense like in a good way and prevent from this noise channel?
I think that's a good question. I think it might be possible. One way to think of it is that to get like a good sensor, you want to have a unitary evolution so that you can get the quantum advantage of this like a Heisenberg scaling. And if you could let that Hamiltonian to induce a unitary evolution in some code space of your bosonic code, while the code can also correct those errors without correcting all the signals from the Hamiltonian, then you will be able to achieve such a design. And on the other hand, it's pretty challenging that to find a practically relevant Hamiltonian, which is not fully spanned by the error. Because one thing we learned from this error corrected sensing is that actually, if you want to measure frequency shift, like A dagger A induced such a evolution, is actually unfortunately in the noisy span due to photon loss, because the noisy span goes to the quadratic of those jump operators. So for that case, we might not be able to do it. But if it's Kerr effect, it's a quadratic, and it's not in the quadratic span. So then you can do it. So it depends on the nature of the Hamiltonian. Yeah.
Got it. There is a question from Shruti about asking you to comment on what Bosonic code you think is best for a particular platform. Do you think, for example, that GKP is better suited for trapped ions, CATS, binomial?
Well, I think it's still open question, and it's still too early to say which platform will be best, and also which code will be best for different platforms, because it all depends on like, okay, I think that even we have numerical evidence that GKP code like can really correct more errors, in a sense that ideal operation will give you better entanglement fidelity at the end. On the other hand, it doesn't mean that the practical implementation will give you the best performance, because it might be extremely challenging to implement those error recovery or even encoding operations. So I think it's still a question that it really depends on, okay, whether we are smart enough to come up with good ways to implement these encoding decoding operations. Yeah.
All right. So if you don't mind, I have a last short one. You mentioned Serge Rosenblum and Philippe Reinhold scheme to do fault-tolerant error detection using 3 levels of the transmon. Should we connect this kind of scheme with the flag qubits formalism, in the sense that it seems more like a polynomial suppression versus like maybe the bias noise ancillas might reach like an exponential protection against the error that like the transmission of error to the Bosonic code?
Yeah, I think that's okay. I need to think about it like the scaling, whether it's polynomial or exponential. Like for this case, one possibility is that you may have we're talking the reason that this bias preserving gates give you exponential suppression is actually you have a higher dimensional like a system, which allows you to have like a higher order error space still preserve the information, right? And if we could design something similar in our Ancilla system, and then that probably would also allow you to achieve higher order suppression of errors for this approach. But on the other hand, I do see like there is an advantage of doing reservoir engineering, because you don't want to spend all your valuable resources of FPGA and those adaptive controls to just correcting error, which is kind of like a common error that's happening all the time. So if you could have a reservoir engineering can save you all the resources, then that probably would be a good thing to do, because actually those error syndromes, it's not that useful information. It's just useful only for error correction. Other than that, you don't want to know it. You probably will better to forget it after error correction. So that's why I think that if we could do reservoir engineering, it might be a potentially advantageous thing to do. Yeah.
I see. Okay, thank you for these comments. So let's thank Liang one more time for this great talk. And next we'll have Raphael Alexander from